This is going to be a different flavour of the other talks today. This is a basically a talk on current work on CPDN. CPDN is climateaddiction.net. David, Professor Dave Wallum spoke about this last week, and I think he just gave an overall direction, where things are going. This week, in this talk, I'm going to be talking about expanding into multimodal. And multimodal, adding adding more models into what we use to compute with. So to date, can you see the left hand side as well, or do you just see the full thing? Yeah, it's better
yeah, we can see the left panel.
Is that better?
Well, now we're seeing a presenter view, so we see the current slide, but also the next slide. So that makes the current slide quite small.
Okay, I'll leave it on this one then. Right. So to date, the climateaddiction.net project has used the UK Met Office parameter models. These are HAD-CM3, HAD-AM4, HAD-AM3P, and HAD-RM3P. These are notably the including notably the HAD-AM3P, HAD-RM3P set of models which come under the Weather at Home subheading, which has been long running now. So these models have enabled 3 types of studies to be conducted: extreme event attribution, the change of likelihood of extreme events occurring, bias reduction, and climate sensitivity. That is the mapping of plausible ranges of climate sensitivity. However, these models, we cannot do either. With these models, we cannot do either seasonal forecasting or fine scale modeling. So to that end, we've been working on adding 2 new models in: OpenIFS model and the WRF model, to correct for that's missing. So when considering adding a new model into CPDN, we need to make a couple of considerations. These considerations fall broadly into scientific user considerations and technical considerations. We need to have a model which has a large community of scientific users and that will produce scientifically useful tiny results. And we need a model that's available for one of the CPDN project's supported platforms of either Linux, Windows, or Mac, and a model that's portable and does not excessively use network bandwidth of volunteers. We use so OpenIFS is the open source version of the IFS numerical weather forecasting model. This has been produced for universities and institutes by the European Centre for Medium Range Weather Forecasting, ECMWF, who have produced the IFS model. It's portable, designed to work efficiently across a variety of computer systems, and it produces the standard GRIB format files. They're optimized for low data transfer rates. It has a large community of users of active atmospheric scientists, and as such, OpenIFS is very suitable for inclusion within CPDN. In the work of this project, we incorporated OpenIFS into CPDN as the OpenIFS at home subproject. This project enables large ensembles of weather forecasts to be run in the CPDN project, providing a new platform, a new and novel platform for scientific experiments. In order to do this incorporation, a number of adaptations needed to be made to the OpenIFS model. The MPI library needed to be removed, as parallel execution is not needed. This reduces the memory footprint and the size of the executables. Model restarting capability needed to be added in order to handle the stop-start behavior that occurs on volunteers' machines, and a change needed to be made to allow larger ensembles of greater than 255 members. So the OpenIFS at home now enables a large number of new experiments to be conducted. Large ensembles for studying the predictability of weather forecasts, the exploration of interesting weather and climate events by testing sensitivity to physical parameter choices in the model, studies of probabilistic forecasting chaotic atmospheric flow, and current OpenIFS experiments can be run in OpenIFS at home as well. So to do this, we needed to do a validation of this work. So we we did this using an ensemble of Storm Karl. Storm Karl was a weather event that occurred in September 2016 in the area between Scotland and Norway. In this experiment, we ran an ensemble of 2,000 members. This ensemble was computed within 4 days by the CPDN volunteers, a time frame which is scientifically useful. So there's a little map there of the showing the precipitation. The results from this validation experiment were compared to previous simulation results from OpenIFS, produced on the using WF HPC machine. The results from OpenIFS are shown on the left-hand side, provide the same results as OpenIFS runs shown on the right-hand side, which have been produced using the HPC machine. A large number of runs of OpenIFS provide a greater detail of results. These results have been are in publication. They're in print in the Journal of Geoscientific Model Development. So now looking at the OpenIFS WRF model, the WRF model WOLF has been produced by a collaboration led by BOINC in the US. It's a next generation weather prediction system designed for atmospheric research and operational forecasting. It's open source and provides a wide range of scales. It can be used for simulations using real actual data, idealized data, or for operational forecasting. In terms of WRF's model suitability for inclusion into CPDN, it has a large worldwide community of scientific users. It has portable executables which run on a Linux machine, one of the supported platforms. It's a Fortran application and available for a number of OSs, compilers, and different hardware. WRF Wolf in CPDN enables new experiments. It enables finer scale simulations to be performed and enables problems in uncertainty that cannot currently be explored to be by the WRF community to be explored using this paradigm. A key component of this work in the presentation has been design and production of a bespoke control code for the OpenIFS and WRF models. This code handles the operation model of running on the volunteer's machine. It handles the communication with the BOINC client and handles the parameters, file structure, and all states of the volunteer's machines. This code is open source. This is a generalized picture of the control code, which is with the BOINC client in the model and controlling the model and the setup of the models. In terms of future steps for this work, we need to do a validation experiment for the WRF model in the CPDN. We will be porting a more up-to-date model of the OpenIFS, the 43R3 model, into CPDN, and looking at the combination, combining the two models linearly. So that is OpenIFS model, OpenIFS at home models feeding directly into WRF. Currently, we have the Hadley models in Linux, Mac, and Windows. So far, we have the OpenIFS model in Linux and Mac, and we only have the WRF in Linux. So we're looking to expand that out at the moment. So in conclusion, we've successfully incorporated OpenIFS and WRF into the CPDN project. We've performed validation of OpenIFS at home using the example of Storm Karl. These results show that these results can be produced in a scientifically useful time frame. This work has enabled eventually capability for scientists. OpenIFS at home enables very large ensembles of weather forecasts to be performed. Studies that previously were too expensive, and WRF enables finer scale models to be run. So, and finally, thank you to all the volunteers for doing the computation so far on these two projects. So.